Hello, my name is Suhas Vaturkar. I did a project for the big data analytics for streaming, Spark streaming. Uh, Before I go deep into the streaming part of the presentation, let's quickly review what Spark is. Spark was originally developed by UC Berkeley and it became recently an open source project, and it has a lot of advantages over the traditional powerful tool sets that we have, MapReduce, Hadoop, or even Storm. It has a lot of advantages. That's why Spark is gaining a lot of attention from the big data community. So overall programming model is much simpler than Storm and Hadoop. MapReduce. The Storm components can, rather not Storm, Spark components can be interchanged for batch interactive and near real time as well. Now this is a very distinction. This is what it differentiates Spark from others because meaning Hadoop is popular for batch processing. Storm is popular for stream processing, but they are entirely different modules, and as a matter of fact, it may need two different sets of skills to maintain that as well, which is not the case in Spark because the streaming part of Spark is based on uh, the core Spark, which is used by batch as well, and so on and so forth. It does integrate closely with HDFS and Hadoop, and its architecture is based on RDDs or resilient and distributed data sets. I'm not, because of lieu of time, I have lots of slides to cover, but I'm going to skip the Spark batch part. Except I'm going to give a quick illustration and then we can move to the Spark streaming part. So this is a quick comparison between a MapReduce job and a Spark job. So we always will start with a slow IO-based, IO-bound data store. And in typical MapReduce, we run off iterations of MapReduce jobs, right? So to get the data for this iteration, it has to do IO operations to get the data. Once that is performed, what is completed, it is going to need an IO to write the data out. And moving on, it will all of the intermediate steps they are going to rely to ingest and digest the data. They are relying on IO, and obviously this is big data, so it is going to take a lot of time to perform those IOs as well because over a period of time the disk speeds have not caught up with the rest of the computing speed. Now, on the other hand, Spark is slightly different. Again, we have to start with a slow data set, uh, and it has to do first IO. But once the first IO is done, rest of the intermediate results are stored in RDDs, which are mostly in the memory objects, and they have a way to spill any overflow to disks as well. So as we see, a lot of overheads of IO is eliminated or at least avoided in Spark. That's why Spark is known to be much faster than traditional MapReduce IO bound jobs. So to give a quick introduction on Spark streaming, it's worthwhile to mention at least what do we mean by streaming. So in batch mode of operation, we work on a like defined set of data, and once that data is processed, the job terminates. Now in streaming mode, though, that's not the case. Streaming mode, the data is constantly coming, and there is no end of transmission or end of data set because it's constantly coming in. And many times you have to process such data sources 24 by 7. So the programming model is much considerably different in the in streaming mode. So we can give an example is sensor data that we receive that we have, or tweets or social media activity. These are all examples of stream data sources. Now, Spark streaming modules basically extend the core Spark functionality for processing large scale of stream data. And most of the reuse comes by it, they create or they treat a stream data by as batches or as micro batches by simply chopping off the data between time slices. So from time one, like I said, from T1 to T2, whatever data they receive, they treat it as batch one, and batch two is from the subsequent time slice, so on and so forth. So at the same time, they keep the batch size like very small, right? Like typical batch slice, rather time slice is between around 500 milliseconds to a second. So if you have a 500 millisecond batch size, you'll get a latency of around say 1 second, which is still okay for the size of the data. So as I said, Spark streaming is an extension of the core Spark functionality to process streaming. Out of the box, it provides support for following stream types: the Kafka, Flume, HDFS, S3, Kinesis, that's a newcomer on the Amazon side, and Twitter. And the micro batches are represented in the Spark programming language or a model by what they call it as discretized streams. So we'll come to that shortly. Discretized streams or D streams are an abstraction for a set of RDDs. So if you look at the batch model, when you open a data set in a batch mode, we get RDD. RDD is nothing but one representation of the whole distributed uh, data set. Now, D stream is a collection of RDDs, and each RDD pertains to one time slice. Period. Uh, and then they have a disk stream can be created from a streaming data source, or it can be created by transforming another disk stream as well. And the transformations are standard that we are all aware of: map, join, flat map, so on and so forth. And the output operations also supported for each RDD. It will let you iterate through the RDD, each RDD within contained within the disk stream, uh, print, etc. So let's talk about a first example, and then we can. I'm going to quickly switch to my IDE to show the code that is working as well. So the use case is we are constantly getting streams of data, and each record is considered one delimited by line feed. And what we need to do is we need to only output lines from the stream which contain a word God. So that's what the use case is. We'll use these streams. I don't want to go to the whole slide, but it might be a good idea to simply switch to IDE and show this code working. So here is the POM file for a streaming module. Now, it looks absolutely similar to the batch, except we inject a dependency for Spark streaming. And let me quickly take a look. So, Spark streaming depends upon Spark core and rest of the common libraries. So, everything, meaning at the dependency level as well, we don't have to worry about injecting other dependencies. That will be taken care by Maven. And let's take a look at the quick Java class that we wrote for the first streaming program. So anything that is interesting starts in obviously main. We check the arguments. If all the command line arguments are in place, we create a Java Spark context just like any other batch program as well. And this is the slight variation where we create a streaming context now, and the streaming context needs to know what is our duration. So what is the size of our micro batch? So once you create this, next thing to create, like we get RDD in batch, we need to get a D stream, and in our case, we are just going to create a plain old socket stream. Now, this could be uh, again. This could be a Kafka stream, it could be Twitter stream. The moment we get this Java D stream, rest of the functionality or the coding will remain the same. So in our case, we are just going to accept that stream and look for all lines which have the word God in it. So we're applying the filter transformation, and finally we print whatever we see as the lines with the God. So let me quickly switch to my console view and we can see this code working as well. Okay, to show the streaming program in action, I have opened two windows and then let's me, okay. Yeah. So what this command does is it just opens a listener and you can just type in, it will start posting, and this job, our Java main program also is going to listen to the same port. So anything that we are going to type in here is going to be available to this, but again we are filtering, we are looking for lines with the word God, and if you look at it, it is uh, showing a time slice of 1 second as well. So let's go to. If you look at it, we inputted a lot of number of streams, but only the ones with the word God will be essentially outputted. So this is a quick demonstration of the filter transformation on a continuously feeding data where you create batches and rather you create time slices, and every time slice is treated as a batch as well. So one thing we need to quickly introduce is the window operations on these streams as well. Now, the streams are nothing but constantly received data, and instead of processing it continuously, Spark divides it up on batches of data. Now, each batch, now you can collect a number of batches to form a window, and that window can be sliding as well, so that you can get some kind of sliding moving averages as well. And now, this is just best explained by visualization as well. So, let me quickly switch my view to the visualization that I created. So, let's take a look at a quick sliding window example. So in this illustration, the red boxes are the time slice. So this is time one, time two, so on and so forth. And the boxes below, they show the count. Let's say, or this is a representative of a volume or extent of streaming data that we received. So for in our example, on time one, we just received one tweet. On time two, we received seven tweets. Time three, nine, so on and so forth. And our intent is to measure or count the total number of streams received in a window of 5 seconds. After 5 seconds, the window resets. The again, so the first time slices goes out of scope, and time slice 2 to 6 become the window. So it can be quickly given illustrated by this example. So now we have time number one. So I'm considering this one. Now this one, just to so that we all understand, this one is not something stored in memory, but like RDDs, they have to do some real work to get that thing in as well. So moving on, I'm going to the second slice. I received 7 tweets, 9 tweets. So if you look at these boxes, they're adding these numbers, but this box is doing slightly different thing than the other one, but I can explain that as well. So moving on, this is the full window size. So we occupied all the window, and then when we move, then we are just discarding this number one. So to get the total of this box, what it is doing is it is simply taking all of these numbers and adding. Although this box, what it is doing is it is adding the number that we got or we gained, and it is subtracting the number that we lost. So now the current total is 26. We are getting 7 and reducing 7. So now here nothing will happen. Like 7 minus 7 is 26. But here we are adding that number 7 again. So these are two ways of processing a sliding window in and then in Spark terms or Spark streaming terms, there is a once very simple function that we can use that supports the sliding operation. So this is a sliding function sliding window in action. Again, I'm going to use some real Twitter data, and then let's quickly go to the code. Again, in the main program, we check for arguments, create the Spark context exactly the way we did earlier. Now, another next thing that we do is we create a Java disk stream from tweeters or tweets. So there is a API called twitterutils.createStream, and we have to pass the Java streaming context. That's it. It by writing one line of code, it will subscribe. It will feed. It will connect to the Twitter web services, REST web services, and start getting tweet data. Now, next thing is it is going to, let's not really worry about it looks complex, but all it is doing is it is rather it is splitting all the hashtag entries that we received in each tweet. And again, we need to, for the counting purpose, we need to assign a value 1 to that. And this is what we are talking about, reduced by key and window. So it takes two durations. That's very easy to see what is the window duration and what is the sample duration. In our case, window duration was 5 seconds. The sample is, I believe, 1. And and what it does is it takes two functions. What do I do when I gain a number, and what do I do when I lose a number? So by writing this code, it is doing exactly the same thing that I showed in the quick illustration as well. So let's quickly go to a console and run this program to see what exactly. So let's see the windowing in action. Let me start this job because it takes time to warm up. So this the Java class that I showed, it is configured to for a window size of 5 minutes, and the sampling is every 10 seconds. So as you see, every 10 seconds we'll get a new set of data shown to the window. And initially everything will start with 1, but it will start accumulating till we reach 5 minutes. After 5 minutes, it will again it will lose the older data and it will add newer data as well. So this is how a typical window transformation in DStream works. So let's talk about DStream stateful transformation. We just looked at a window transformation where you can use sliding window to accumulate certain numbers, but for stateful transformation is slightly more interesting than window, where let's say we go from T1 to T2. So at T2, we have access to the data or the state of a key at T1 as well. and then based on that you can aggregate or any other you can take for further actions as well. So it's explained we meaning if you take a use case, instead of doing a sliding window, if you want to have an all-time high count, then we can use the state and transform every time the numbers or the state that we have earlier, just add to the current state so that we get all-time high numbers as well. The most of the code is going to look the same, except we will be using something we will be implementing something called an implementation of a function to interface. It will be calling the update state by key functions. So let's go to the next page. So the implementation ultimately will call the will implement a call function. The first parameter is list of integers. These are the old or historic states. That's the v1. V2 is the current state, and then output is the combination of these two. Now it could be a much more clearer if I switch to my IDE to show this code as well. So let's take a look at the implementation of the function that we talked about. It's this update function that we are talking about. It is implementing the function to interface. The first parameter is a list of integers. That is the historic data. And the second parameter is the current data set, what happened at T2. So this is what happened at T1. And this is the return type. So the implementation of that is like now we understand it's really simple. So you get a list of historic data, you get the current data, and you are expected to return the integer. So you just take the first return of you just accumulate v2 integers v2's value as the return val, and now optional will tell you if that is optional or it is null, it will be simply returning 0. Now for integer I and v1 we are just going to take the historic data and just add repeatedly to the return val and return the return value back to the caller. So this kind of implementation, if you plug this function in into the update function, what it is going to do is it's going to start accumulating the timestamps for the beginning of time as well. So this is a quick demo of or not this is a quick code walkthrough of a typical a stateful operation as well. Now in lieu of time I'm going to quickly skip this demo, but what you would be seeing is instead of the numbers will just keep on growing without getting tripped at the when the window size is left, the window size is reached. So just to conclude, I'm going to show an example of again the same use case, reporting on Twitter data. In other example, what we were doing was we were directly connecting to the Twitter stream, and the way these streams work or even RDDs work, if any data that is lost because of failure, it reruns, goes to the lineage to process the data. But this works if the input is reliable, and stream data source by definition is unreliable, because once if you lose a stream, you cannot go back and recreate that. Uh, so a best practice for streaming data is first when you receive a stream, persist it on a fast queue like Kafka. Now more recent is Kinesis that is offered by Amazon as well. So if you do that, what happens is if we have a failure, then we have something to go back to because we have a reliable queue. And then process from there. So in the example that I'm going to show, we are going to have a producer, a writer, which is going to simply take a streaming data source, subscribe to a stream, and put it on a queue. And it's done. So and then the another job, what it is going to do is it is going to look at the queue and process. Now uh, paradigms or products like Kafka or Kinesis, they are very fast. At the most, they may add a second, 1 second of a latency, but that latency is worthwhile if you want to have reliable processing of data as well. So, without further ado, let me quickly switch to my IDE. So, as you see here, I have two projects here. First is a Kinesis writer. Let's take a quick look at it. So it has two or three classes. This is very small. One is the Twitter producer. So what it does is in the Java main, this is a boilerplate Twitter client code. So what it does is we are supposed to create an instance of or the anonymous instance of status listener and provide a on status method and then if you wire rest of the things you create a Twitter factory and add this listener to that and start sampling. What it is going to do is it's going to establish a connection to the Twitter web service and then start ingesting those messages, and that's what we are going to get here in the on status method. So that's what it's going to do. Now once we get in any message, what only what we need to do is we need to post it to Kinesis. So there is this call that we do writer.send transformation, meaning it will just create a JSON object and put it to the Kinesis queue. Now there are certain setup that we need to perform for Kinesis, but the steps are absolutely there on the Amazon website. And with the project's supplemented documentation also, I have provided exhaustive steps how to create a Kinesis queue on Twitter or not on Amazon as well. So once we get a tweet, what we do is go to the Kinesis writer. We create a new Kinesis writer, and all it is doing is sending that to the queue. Now this is not Spark streaming, so I'm not going to go much detail into this code. So all the concern of this job is to subscribe to the tweets and put it on a queue. Now the consumer part, again, it's not that complicated as well because most of the functionality is handled by uh, the framework code anyway. So this Twitter hashtag analyzer, what we have is this is a traditional like Spark streaming code. So we have to first create a Kinesis client, and then so that it knows all the endpoints and everything. Once we have this Kinesis client, again the same thing. We create a Spark config and create a Java streaming context from the Spark config, and then create a byte array Java distrim from the Kinesis util. This is the out of the box connector available in from Spark. Kinesis util create stream. You pass certain useful parameters like streaming context, stream name, endpoint, duration, so on and so forth, and that from that point onwards the rest of the code will look exactly the same. So what we are going to do is we are going to get all the streams from the queue, and then it is simply going to start reporting just like any other streaming program. So let's quickly go to the demo of this code. So I'm going to switch back to my console view. So for this demo, I have already started a Amazon EC2 instance. I already downloaded, meaning this I as a part of the Bootstrap, I added the Spark steps as well. So Spark is installed here. I had to little bit do some setting for the class path, not class path, the path, and logging for the Spark. But other than that, the out of the box implementation of Amazon Spark is in use here. So I created a directory. So for this project. So let's see what I have here. Okay, so I have only one jar here, rather. So let me start this program. So what it is doing is it is simply connecting to the queue, and look at this. It started spitting out timestamps. That means it is showing that, hey, between this T1 and T2, I didn't find anything. Now our Twitter producer program, what it is going to do is it is going to uh, get instance of the Twitter factory and add the listener that we created and then start tweeting. So let me start this program. Now this thing, there was something left over. I might have run earlier as well. So what's happening is once this start once this class starts executing, it will start. Yeah, it started putting a lot of tweets to the queue, and now you will start seeing. Yes, you will start seeing. So now this is running on my local, right? And this is the real Amazon instance. So from here, I'm creating a URL connection to the Kinesis endpoint, and all these tweets are sent to the queue. And this thing, again, it is not reporting everything, but this thing is throttling those tweets and showing those to the queue as well. So this is one of the best practices to use, create, or process streaming data, where what happens is since all the tweets that we are or the stream data that we have is being stored to a like a reliable queue. If any of the RDDs or if there is any failure, then since the data source, input data source is reliable, the overall processing can be guaranteed to be fault tolerant as well. So that's what I had from my side. Thank you so much for your time, and good luck to everybody. Thank you.